So, like I said, this is what happens when you submit 2 proposals and they both get accepted. So at Ampere, I really kind of focus on profiling on hardware. I work a lot with the hardware teams and microarchitects on performance. So I like to take a look at all the applications. You know, how can we make sure they run better on our ARCH64, and how does that affect our own hardware performance, and how do we compare to x86?
Actually, can I ask a bridge question for both of you?
Yeah.
You might have already covered it because I was late, but you might cover it again. Like when you're profiling JITs, like do you have synthetic testing that you rely on to get the profiling to figure out how to speed it up, or how do you get real world test cases or scenarios, or do the synthetic ones do it justice?
That's a really good question, because each is different. When you work with OpenJDK, you can use JMH, but there's caveats with JMH because it's very difficult. OpenJDK is a very large piece of software. And likewise, when you're working with HHVM, you don't really have a large ecosystem with HHVM, so I don't really have any other options. I can kind of look at PHP bench and I can see how well I'm doing with PHP, but that doesn't help you with HHVM. But you're right, sometimes it depends on the JIT. In the case of Java, you do have that sort of, you have JStress, you have JMH, and you have some other tests as well. And that's always good, but it's always the caveat is to make sure that is the problem you're seeing representative. Because that's what you want, absolutely. If you can take some performance issues you see with OpenJDK, and you can then create a micro benchmark of those that can facilitate your own improvement, but also facilitate upstreams. That's my goal. I always try to break things down a little bit to find out where the problems are. So OpenJDK benchmarking, SpecJBB. It's a usage-based worldwide supermarket, and it handles a mix of point sale requests, online purchases, and data mining operations. So it has both a throughput metric as well as a time-sensitive throughput metric as well, which creates based on hypothetical software license agreements that said it needs to be within 10 milliseconds to 100 milliseconds. It supports multiple run configurations, so you can analyze and look at a lot of different things. You can do very short runs, or you can do full runs, full reference runs, for example. But it gives you that flexibility when you're working with it. How to approach it? So understanding your performance on Java, I kind of look at 3 areas. One is, I'm looking at the hardware. Is ARM architecture worse than Intel? You know, where are the gaps there? Is it, you know, is it the traditional weak versus strong memory model? Is it our lock handling? The other thing is your SoC microarch worse than ARM? So you've got 2 different things. You're looking against Intel, but also if you make your own product, you want to see how well you're doing against the ecosystem as well, and ARM's own reference. And then from the software side of things, you want to say, is Java optimized for Intel better than ARM? Look at the C2 code generation and optimizations. Look at the garbage collection. Again, that's kind of that sort of scan to see what changes have been made there. It's a lot harder to do that with the code base because there's different garbage collectors, but again, it's an important survey to take. And then, is Java optimized for ARM? You know, using software monitors with safe points to analyze some of your performance, and using JStat to look at some numbers on how well you do and in regards to your own design. And can we measure better? You know, you want to look at your SpecJBB parameters, your disk, your memory users, which GC are you going to use, for example? And you have to be careful too, is your garbage collector reflective of what customers would actually use? You know, that's another big question too. But in a way, working with OpenJDK is a lot of data mining too. Yes, do you have a question?
Yeah, sorry, it's along the same line, but can you comment on, like, if you don't want to, but SpecJBB versus like real world scenarios, because this is everything written in Java where today, you know, you have containers and different pieces are all over. Some might be Java, some might.
Yeah.
This is just one thing, and it's not, you know, it's not not necessarily indicative, and it's fairly older. Like, how well does this represent, and is it good enough to where?
Yeah, I think it is important because there are a lot of Java applications out there. This is just one, but obviously it's a big one because a lot of people depend on it. But there's things outside of that that you could look at that are based on Java as well that might give you representative. So there's like third-party applications and so on that may use this that you could take a look at. But in terms of it, in the end, it's a synthetic benchmark, right? So that means it's part of engagement with the customer and understanding also from customers, find out what are the applications you're running, and is this indicative of yours? So just like HHVM, unfortunately, I feel like I'm analyzing an onion that I'm peeling back, but to some extent it's a synthetic onion, right? Keep that in mind. But I'm kind of selfish because I'm looking at it from the point of view of hardware architecture too. So I don't have a good answer there, but I don't think it's fully representative of real-world applications. So where to look in software? So garbage collection. Well, garbage collection, you know, your critical JOPS might be a good test for garbage collection issues. Evaluate variation in heap and impact on performance. Compare various garbage collection models such as parallel garbage collection. The other target to look at is the just-in-time compiler. Can you achieve your max JOPS performance, you know, without the best level of JIT optimizations, right? So that's kind of a trade-off you're seeing is that do you feel you're being limited or not? And also take a look at, again, changes to the JIT. Do some analysis on your own. Safe point sync. So do you have problems with the safe point sync, which is basically having your threads move to a safe point based on the garbage collection's readiness in terms of being able to move, being able to start moving memory? And can all your threads get moved to the safe point? And software monitors can help you look at the safe point syncs. Another area I was kind of curious about was string instructions. Intel uses string intrinsics for compression with regards to their string usage. And in some of my testing, I didn't really see a big boost for x86. But then again, just a caveat there. But it's just one area to look at. And I know ARM has talked about, you know, string optimizations as well. Encryption instructions. Evaluate your performance change when encryption is turned off and when all transactions are encrypted. Now, in this test, all transactions are not encrypted. But if they are, think about your data width. You know, do you have like 256-bit width for your crypto, you know, AES-NI instructions, or do you have a much limited reduced width for your data? Because that's going to affect your throughput. So keep in mind, like OpenSSL speed tests and things like that that can point to areas where you might have some gaps. Where to look in hardware? L2 cache. Understand the topology of your system. I once saw a bug on a 32-core system that thought it had 16 NUMA nodes over with 2 sockets, you know, when in fact it's actually a single socket 32-core system. And that was a kernel bug. But imagine if you do that and then do a test and think like, why in the world am I getting this data? It thinks I have 16 NUMA nodes. But things like that you need to pay attention to. That's your topology. But also your L2 cache. Is your L2 cache within the core, or is it shared between 2 cores? You know, your TLB, heap size, shrink, decrease miss rate, and measure performance. You should see reduced performance as you shrink your heap size because you're kind of hammering the TLB. But look at your TLB as well. I have some further insight to add to that later. Then also dependent loads. Loop with dependent loads. What portion of the top functions profiled have this issue? Create some micro benchmarks on that in terms of your dependencies. Because keep in mind with x86, like with a lot of ARM systems, they might say, you know, you're restrained on loads by your 2 oldest loads, and until those 2 oldest loads are taken care of, you have some constraints there with ARM. With some ARM architectures, newer ARM architectures might have allow greater than 2 loads. Look at transparent huge sizes and page sizes. variations in terms of your workload. Memory barriers, use of data memory barriers in the absence of LSE atomics. If you're not an 8.1, then maybe you're using DMBs, right? And DMBs can be expensive, right? Somewhat, and also it depends on your own microarchitecture in terms of to what extent they can affect your execution. But again, look at, and this is all part of your profiling as you're looking at, some of your execution. That's where TC print, not TC print, but in this case, O profile or J profile, and looking at annotation. Scaling with course, again, my example with topology and your cache model on linear scaling with course. So as you scale your course, how well do you perform? So when you're capturing this data, are you taking advantage of perf? With the JVM tools interface, you can use a perf map agent with perf in order to get the additional instrumentation. Or you can use O profile, which has built-in support for JVM TI, or J profile, or Operf on JMH tests, and compare hot methods with x86. So that's where I talked about micro benchmarks. So when you're seeing these hot areas, and you maybe with perf you're able to profile some areas too, then try to either use JMH or try to come up with some micro benchmarks that exhibit that same behavior you were seeing. You visualize your results with flame graphs from the generated perf data. Another interesting tool, which if you're licensees of ARM's DS5 tools, you can actually use the Streamline tool and actually run that as a real-time sensor. It's kind of as a real-time visualization of your perf data, which is kind of nice. I've used that before. Or it can also be used to post-process visualization of your perf data. So imagine your perf data, you have your hardware counters, right? And you want to visualize your hardware counters that you've selected or your kernel events you've selected. Well, Streamline's a great visual tool for that as well, in addition to flame graphs. Understanding the data, analyzing your results from a hardware perspective, understanding your microarch relative to ARM v8 supported features, such as data memory barriers, core topology and interconnect, or atomics if you have atomics. Characterizing your microarch features and their impact. Look at your L2 cache model. Again, some interesting tests. If you have a PMD that shares basically 2 cores sharing an L2, why don't you disable every other core and look at your performance and do a 16-core comparison with, say, a silver with 16 cores, and look at your comparison and see how much your L2 is affected by the noisy neighbor scenario, right? Because each of your cores has to share a single L2, and that may be impacting your performance as well. Your L3 cache model. Is your L3 cache a true victim cache? In other words, it gets cast outs from your L2, right? So you can get a lot of insight to how well you're doing based on a lot of the hardware counters you're working with. And in comparative steps, applying you can also look at, like, for example, if you don't have LSE atomics, you could actually go take a look at an x86 and insert M fences everywhere that a DMB might get inserted on an ARM system. And you might see the same reduction in performance, right? You might see some comparative changes. Again, all of it is trying to give you insight into how well am I doing based on this application versus the competition. And then generate the micro benchmarks from these tests for use in your future microarch models to keep a check on regressions and hopefully mitigate it in those future designs. But anyway, that's what I wanted to just cover with you. Just kind of, this is a birds of a feather kind of discussion, and for me it was interesting because I wanted to talk about working with these applications and looking at it from a hardware perspective, and also thinking about, here's how I went about looking at this hardware, comparing it to x86, and sharing my approach and my ideas. But my ultimate goal really is for us to be able to make ARM64 successful across the board with these applications as well. Thank you.